Nonlinearity in structures brings in some challenges that are really hard, and they're almost wicked problems. And what's happened in recent times with the rise of offshore renewable energy systems is that nonlinearity has become a major problem and a major challenge in this sector. So, what we're doing is with Bekaert International, with Seevani Bali, we are modeling nonlinearities in ropes, which are really important in this sector, using a finite volume formulation.
I work on creating numerical models for slender structures like mooring cables or marine risers using nonlinear beam theory. It is supported by Bekaert International, a wire manufacturing company, and SFI MaREI. If we take an example of a marine riser or mooring cables in sea environment, the risers have the potential to incur large displacements, bending and twist. In such scenarios, modeling them as beams can provide an accurate representation of their behavior. A simple numerical theory like Euler-Bernoulli beam theory, which is used for modeling beams in structures by civil engineers, will not work here because they assume that the beams can only incur a small deformation. For structures like marine risers, the case is exact opposite, as they incur very large displacements and rotations when subjected to a wild sea environment. So, I use a more generalized and nonlinear beam theory called geometrically-exact Simo-Reissner's theory to model such beams, which not only takes into account their large displacements but also rotations, and hence we believe that such representations would provide a more accurate information about the nonlinearity of the forces acting on the risers and mooring cables. We are trying to create a numerical solver to capture such beam deformations using a finite volume approach